Hi everyone, welcome back to my YouTube videos. In this video I'm going to tell you about existence of interacting particle system defined on infinite lattices. I quickly remind you from something that we mentioned in the previous videos, is the fact that because you have infinitely many sites, that also means that you have potentially infinitely many updates in any finite time window, and so that means that the time to the next update does not exist for interacting particle system. That's why whether those processes exist or not is absolutely not clear. So the proof I'm going to give you here only applies to the contact process. I'm just using the contact process as an illustration, but it turns out that it's very easy to extend the proof to any interacting particle systems as long as the total number of possible colors per particle is finite. And so to proceed, we are going to use two ingredients. The first ingredient, the main ingredient, is going to be the graphical representation of the contact process that we defined in the previous video. And the second ingredient is a result that we proved in a previous playlist about bond percolation in D dimensions. So to prove this result, we are going to follow the construction explained in the slide here. We are going to fix epsilon strictly positive. Epsilon can be whatever for the construction, but ultimately to prove the result, we'll need to take epsilon small possibly. We are going to also fix a graphical representation of the contact process. I'm going to quickly remind you what it is. And we are going to declare each edge x, y to be open if and only if in the graphical representation there is an arrow going from either x to y or y to x. That way you are going to define a collection of open edges, exactly like for bond percolation in D dimension, and you can, like for bond percolation, define the connected components of open edges that we are going to call in this case islands of influence. And looking at the size of those islands of influence, we'll be able to prove the result. So before we prove anything, I'm just going to draw a picture to show you what's going on. So I quickly remind you that to construct the contact process, you start with the grid, ZD. So here I'm just going to do that in one dimension, but that can be in higher dimension. Then you are going to add one more dimension for time. So you have those vertical lines going up like this. And then we are going to have some kind of random directed graph where you have arrows representing the potential birth in the process. Those arrows, they appear at some specific rate. So for each pair of sites xy such that x and y are neighbors, then you are going to have an arrow from x to y at rate 1/2 in the picture, in general 1/2d. Or I should multiply by beta, so beta over 2 in the picture and beta over 2d in D dimension. And so you are going to have things that look like that. So arrows like this. Let's put one more here and one more there, for instance. And so these are potential birth. You also have potential death that you represent by having crosses like that. So that's the graphical representation of the contact process I defined in the previous video. So now let's assume that our epsilon is here, for instance. Let's assume that this quantity here is epsilon. Then the way you are going to define those open and closed edges is by drawing a line here. Okay, and then you look at all the possible arrows that appear before this time, so under the dashed line. And each time you see an arrow, that means that the corresponding edge is open. So that means in this picture that this edge here is open, and also this edge is open. Because those two arrows, they appear before time epsilon. At the opposite, you see that if you look at this edge or this edge, the first arrow appears after time epsilon, so that means that this edge and this edge are both closed. So from that, you can define a collection of, in red here, open edges. I'm just doing the construction in one dimension, but in fact the result we are going to prove is in fact easy in one dimension. That makes more sense to do the construction, at least in our mind, in higher dimension, but the picture would be too complicated. So I just drew that in one dimension. So, and after you can define from the set of red edges that are open, you can have those clusters of open edges, and those clusters of open edges are called islands of influence. Now, the key to prove existence of the contact process on the infinite lattice is to prove this lemma at the bottom of the slide that states basically that we can find epsilon small enough but still strictly positive such that, and this probability says more or less that all the islands of influence are going to be finite with probability 1. So that's a result that is kind of reminiscent of what we saw about bond percolation or percolation models in general. So I'm going to prove this result on the board, and then I'm going to tell you why indeed if we have this lemma, then that's it, we have indeed existence of the contact process, and the contact process can indeed be constructed in a nice way, and there is absolutely no ambiguity in the construction of the process. So I'm going to briefly recall the lemma. So the lemma says that there exists epsilon strictly positive such that all the islands of influence, all the islands of influence are finite with probability 1. I'm not writing with probability 1, but it's implicit here. That's a statement almost surely. So, how can we prove this result? Well, the first thing is to see that from the terminology, we call those edges open. So maybe I can write open here. And so the first step is to look at the probability that an edge is open. That's a quantity that is going to depend on the rate at which those arrows appear. That also depends on beta, but also the dimension of space. And also that's going to depend on this parameter epsilon. So let's do this. First, we see that the probability that an edge, so let's call it, so maybe I can write proof now, that's what we try to prove. So proof. So first, you see that the probability that an edge, so let's call it xy, is open, is going to be exactly the probability that we have an arrow going from x to y or y to x before time epsilon. You see that there are arrows going from x to y at rate beta divided by 2d, arrows starting from site x at rate beta, but they are going to point at y with probability 1 over 2d, so by the thinning property for Poisson processes, that gives you an overall rate, a rate of beta over 2d to go from x to y. You are going to have similarly an arrow going from y to x at the same rate by the superposition property for Poisson processes. That means that the rate at which you are going to see the first arrow going from either x to y or y to x is going to be beta over d. Okay, so that means that the time here to wait for the first arrow going from x to y or y to x is going to be exponentially distributed with parameter beta over d. So the probability that xy is open is exactly the probability that an exponential random variable, I'm just write exp like this, with parameter beta over d is so the time you have to wait is going to be less than epsilon. So we want this to be less than epsilon, and so this is easy to compute. Exponential with this parameter is more than epsilon with probability e to the minus beta epsilon over d. Here it's just a 1 minus that, so we get a 1 minus e to the minus beta over d, and we still need an epsilon, so maybe let me write this more clearly, I'm going to use more space, so that's going to be 1 minus e to the minus beta epsilon over d. Okay, so that's the first step. Now, you see also that Poisson processes at each site are independent. So that means that the probability that this edge xy is open is an event that is independent of the event that another edge, let's say zw, is open. So that means that edges are independently open with that probability, okay? And so that means that we are exactly in the context of bond percolation in d dimension. If you look at the set of open edges, they are all going to be, by the fact that all the Poisson processes attached to each site have the same weight and they are independent, we deduce that edges are going to be independently open or closed with the same probability and independently of each other. So that means that the process is going to be a bond percolation process where edges are open with this parameter. Now, to conclude the proof, I need to go back to a video that I recorded before about bond percolation in d dimension, where, if you remember, we proved that for, I'm going to write this here, for bond percolation on ZD, percolation, let's say in d dimensions, so we were able to prove that the critical value is non-degenerate, meaning that it's not equal to 1, it's not equal to 0. And in particular, the result we kind of need here is the fact that the critical value PC is going to be larger or equal to 1 divided by 2d minus 1. And the idea of the proof was really to look at all the possible, to count the number of self-avoiding paths starting from the origin with a given length. And we saw that, except for the first step, where we can follow 2D possible edges, for all the subsequent steps, so that the path is indeed self-avoiding, we had 2D minus 1 possibilities. That's where this quantity comes from. That's why we have this critical value. So now, the fact that PC is larger than that means that if the probability of an edge to be open is less than this, then that means that there is no percolation. And indeed, we can say that this is less than 1 divided by 2d minus 1. That obviously depends on epsilon, but you see that in this story, beta is fixed, that's the birth parameter for the contact process. The dimension is also fixed, but epsilon is something that we can play with. And indeed, you see that for epsilon equals 0, that's 1. 1 minus 1 is 0. If you take epsilon by continuity, if you take epsilon strictly positive but small, indeed we are going to have this inequality. So comparing that fact that all the edges are going to be open with this fixed probability that can be made less than this bond for the critical value of bond percolation in d dimension, and the fact also that the edges are going to be open independently of each other implies that, I'm going to rewrite that, implies that we do not have percolation of the open edges the way that's defined here. So this implies no percolation of the open edges. Okay, so of course that's not true for all epsilon. Again, we need this inequality to be true, but we saw that if epsilon is small enough, then we are not going to have, then this inequality is true, and so we don't have percolation of the open edges. So now, returning to this statement, so here again, no percolation of the open edges. That means that all the clusters all the connected components of open edges are going to be all finite. So indeed, that proves this lemma. So you see, the combination here is just to use this picture here with the graphical representation, you cut at epsilon, and also use a previous result about bond percolation. And so this shows that because all the ions of influence are in fact nothing less than the connected components of open edges, by definition, that's the way we define those ions of influence, then indeed this proves the lemma. So now I'm going to erase the proof to have more space, and I'm going to show you why indeed this proves existence of the contact process. And again, the proof would be the same for any interacting particle stem on ZD as long as the number of colors is finite. So how do we proceed? The first thing to observe is that if you have two sites that do not belong to the same island of influence, by definition of those open edges and arrows, that would mean that there is no path of open edges going from one vertex to the other one. And so that means in particular that, and that's why we call those things islands of influence, that means that if two vertices or two sites are in two different islands, then those two sites are not going to even indirectly influence each other before time epsilon. So from that, we obtain the following picture. So let's assume that this is the infinite lattice in 2 dimensions, and then we have our islands of influence. Maybe they look like this. Okay? And we know that they are all finite. Okay? And so now we said that the prime is, and so what I just mentioned is that if I take a site X here, and I take another site Y here, then those two sites, even indirectly, are not going to influence each other before time epsilon. That means that the state or the color at vertex Y up to time epsilon does not matter. You don't need to know this to be able to determine the state of or the color of site X at time epsilon. So that means basically that by definition of those islands of influence, to understand, to construct the process, the contact process up to time epsilon and know the state of the process at site X, we don't need to worry about any of those islands, graphical representation or initial configuration, they do not matter. So that means that now, because this island is finite with probability 1, that's the lemma, that means that now in this specific island, the time to the first update and the time to the next update in general are perfectly well defined. Why is that? Well, because now you have a finite set, so the total number, so you have basically a finite space-time box, okay, where the height here is epsilon. You have to think of, you have one more dimension going that way. So you have the height epsilon. The area here is just the number of vertices in this island. So that's a finite set. The volume is finite. So that means that the total number of Poisson points corresponding to those arrows or crosses in this island is finite. So you have basically a bunch of continuous random variables that are independent attached to this island, and so those arrival times corresponding to potential birth or potential death can be ordered in time, okay, chronologically in time, and so that means that this construction implies that so one, you use the fact that to understand what happens up to time epsilon in one island, you don't need to know what happens in the other islands. And second, with the fact that all those symbols, crosses and arrows can indeed be ordered, like you have first update, second update and so on, in your space-time box, those two ingredients together implies that the process can be constructed by induction. So process can be constructed in each island separately, each island separately. So the process can be constructed in each island separately up to time epsilon. And I'm going to precise by induction. So by induction, what I mean by induction is, or I should use the word recursively. What I mean by that is that you just start in this island with a specific initial configuration, and regardless of this initial configuration, you are going to wait until you see the first either arrow or cross, and then you are going to see what the update does. Maybe that's going to kill a particle, maybe you are going to give birth to a new particle, or maybe nothing is going to happen. And then you go to the second update and so on. So that's why we can do that inductively or recursively on the island, because we can order those things. But you see that these keywords, induction or recursively, is not possible on the infinite grid, because again, the time to the first update does not exist. Okay, you have infinitely many things happening in this short amount of time epsilon, and so that means that locating the first update on the whole grid is not possible, so this time does not exist. But then the time to the first update on each island is well defined. So that's kind of the key. You can construct the process in each island separately up to time epsilon by proceeding recursively. So you use this feature. And so what else? So this shows that indeed we can construct the process only up to time epsilon in a given island. That doesn't show the whole story, but it's easy to eventually conclude. Again, because you can do that for this island, and clearly the number of islands is infinite, but countable. You can do that on each of those islands, which means that you can indeed construct the contact process up to time epsilon on the whole grid in D dimension. And then how do you extend that to larger times? Well, what we do after is the fact that we are going to use the fact that the graphical representation of the contact process or any interacting particle system in general is translation invariant in time. So why is it translation invariant in time? If I translate up or down, I'm not changing the distribution here. That comes from the fact that the exponential random variable, that's the time you have to wait to the next arrow, is memoryless. And that's also equivalent to the fact that the process is Markov. So because the process is a continuous time Markov chain, once you know how to construct the process up to time epsilon, then you can just consider the spatial configuration of the process at time epsilon. You rethink of that as the same as the initial configuration, and you can restart from that and again construct on each island the process up to time 2 epsilon and so on. So here be careful, there is just a little twist. The fact that I'm saying you can construct the process up to time epsilon, and then by the Markov properly you can use this restart argument and then again construct the process from time epsilon to 2 epsilon and then 2 epsilon to 3 epsilon. We can indeed do that, but you have to have in mind that after you look at 2 epsilon here, and then the new set of open edges you obtain is not the same as before. So in fact, if I recap, it's really you fix this little epsilon such that we have some inequality and so we don't have percolation of the open edges. Then that that induces a partition of the lattice based on the graphical representation also into infinitely many finite islands. In each of those islands, you can construct the process up to time epsilon. Then at time epsilon, you have to redo the construction and you are going to get a new partition, again, into islands of influence, but this partition is not the same as the one you started with. It's another one, and at each time window of length epsilon, you are going to get a new partition into islands. But all those partitions are going to be of this type, meaning that all the islands are going to be finite. So that means that indeed you can recursively construct your process up to any time. So indeed this construction shows that using, you see, result from bond percolation and the graphical representation we saw in the previous video, combining those two results, we can, and this construction, combining those ingredients, you see that indeed the contact process exists and can be defined without ambiguity at up to any time.